I'm going to share my screen, and the screen that I wish to share will be this one. And I'm going to go to this and this. All right, so like I said, this is a different textbook than you guys are using, but the textbooks are essentially all the same. Sometimes they'll number them a little differently. That's why I made sure I gave you guys practice tests. I wanted you to make sure that even though I'm sort of using the same sort of banks for all my classes, that they do very much fit with your class. But I wanted you to see exactly what would be hitting you each test. So that's why I make the practice test out of the actual test questions, the test banks that I use for my course or for my actual test. So keep that in mind. That's the whole reason why I suggest you guys all take the time to do the practice tests over and over and over again until you can sort of consistently get an 80 or better. If you can consistently get an 80 or better on the practice test, you're in a really good spot to take the test. If you're doing that by using time to look up anything on those practice tests, then you're probably not prepared. But other than that, you're good to go. So does everybody see the same screen that I'm seeing, which is a cool tropical looking island with a rainbow over it?
Yep.
Yes.
Okay, cool. All right. I was pretty sure that's how it worked, but I switched from one tab to the other, so it kind of concerned me. So this is a chapter on light, and there's this amazing thing that happened all through the history of physics and science. We've gone back and forth. For instance, Isaac Newton wrote about 500,000 words on optics. He just literally did all these experiments. You know, he was somewhat of a recluse, so he stayed inside his house for long periods of time. And I'm going to stop the screen share a second so you guys can see me. So Newton was this strange character. He did a lot of things to experiment. I mean, his whole life was about experimentation, as was a lot of people at the time, including, for instance, Robert Hooke. Yeah, I was going for my glasses. They aren't there. But one of the things Newton did is he wanted to understand how the shape of the eyeball affected the light that he saw. So he wanted to know, in other words, how does the shape of a lens affect light? So he had this really cool idea. He pulled his eyelid out and he jabbed a knitting needle in there and then pried it and then drew pictures of what the image looked like. And you can see there there's this sharp point with like lightning bolts striking all out the sides of it. And that's what he said he saw when he jabbed himself in the eye with a needle.
Oh my gosh.
What?
Yeah, he really did that. Not only that, he would stare at the sun for as long as he could, and it became so bad that one time he got a migraine that he had to lock himself in his house for over 30 days with the blinds pulled. So these guys were scientists in the most extreme. A lot of weird things they did is like they would weigh out basically every ounce of food and drink that they took in, and every ounce of solid and waste that they put out. And I mean every ounce. So these guys were pretty intense scientists, and their whole life revolved around science, and they were just super, super curious. Newton also wrote over 500,000 words on the Bible, for instance. He was really concerned about numerology in the Bible and thinking that there was some numbers in there telling us special things that would give us sort of the elixir to life or find the fountain of youth, if you will. Not only that, he drank mercury every day of his adult life, specifically because he thought it would make him live longer. That sounds really bad to us because we like measure the amount of mercury in seafoods that we eat nowadays, and we know it's not a good thing to ingest. But he actually drank it, and that's not an uncommon practice. For instance, we actually know somewhat of the path that the Lewis and Clark expedition took, specifically because we found sort of fossilized poop with mercury in it. So whenever you find that in an area where only the Native Americans were at, or Amerindians, I think is the new catchphrase that academics use, they weren't using mercury for that kind of stuff. So any of that you find from the time period had to have been there. So that's actually how we've managed to figure out how the path of Lewis and Clark went. Remember, sort of Meriwether Lewis sort of lost his crap when he got out there and didn't write anything like he was supposed to. But thank God Lewis took notes and did surveys and stuff like that. And of course, Meriwether ended up with a tragic ending. So anyways, that's sort of the ambition of the scientists of the time, is doing weird things like collecting all your, you know, weighing all the fluids that go in and all the solids that go into your mouth, and then seeing all the fluids and solids that leave, and then seeing if your weight actually changes so they could determine whether there's a conservation of mass. So Newton set back, and before Newton, basically everybody was sort of the opinion that light was a wave, but they didn't necessarily know what a wave was or what it would be a wave of. Newton was going on the idea that light was made of these corpuscles, these little particles of light. And he predicted how these particles of light would behave, and in fact got essentially all the equations we use to this day for optics, he got from treating light as a particle. And they're ideally, I mean, they're essentially the same equations we use now, even though we know light is quite different from a particle. So I wanted you to get that idea, one, about Newton jabbing himself in the eye, but two, get the idea that Newton was able to come up with light as a particle and come up with the laws of physics that are still quite accurate. So the other thing I wanted you to see was that, in fact, there is a way that you can test and see for yourself that light is, in fact, a wave. And it's this: you just take your two fingers and you put them really, really close together. You can start to see it. See how it makes this little line in between my thumb and index finger? You want to put them so close that you're seeing that, and then you look up at a light source. Like I'm looking at the bright light coming from the window. And what you'll see is a repeat of your thumbprint, and a repeat of your thumbprint, and a repeat of your thumbprint, or maybe a repeat of your index finger, index finger, index finger. And that is where light is actually behaving as a wave. Because what happened is the hole between your index finger and your thumb, basically each spot is acting like a separate source of light. So each one of those places have this little wave front coming out, wave front coming out, wave front coming out, wave front coming out. All of the infinitesimally located points, all the infinitesimal points between here and here, which is literally an infinity of them, are acting like separate sources of light. And when a wave crest hits a wave crest, it makes another bigger crest. But when a wave crest hits a trough, it cancels it out. So what's happening is there's areas where you're not seeing any light coming from the sky behind it, and that light is in fact interfering with itself, so it's disappeared, and in goes the image of your actual thumb. So that's a simple experiment you can do to show that light is a wave. So this was a really big deal. We had worked through Newton, and everybody really knew Newton was on fire. He sort of revolutionized physics and kept it still for a long time, and we ran with that. But around the late 1800s, early 1900s, we started getting these experiments that we couldn't quite explain, and we didn't necessarily think they had anything to do with light, but here we are. So I'm going to go over those experiments and talk to you a little bit about what they were before I get back to that slide. So one of the experiments that was being seen or being observed was that when you took a glass tube, so imagine like a test tube, but you cork it off with another piece of glass, and you had a little valve in there, a pipe that came out of it with a valve that could stop it, and you could suck all the air out and then close it off, so it literally be a vacuum, as close as a vacuum as we could get on Earth, and keep that essentially empty. In other words, you might have 100 atoms per cubic centimeter, which is a really, really small amount, right? Suck all that out, and then you replace it with just one gas, say hydrogen or helium or mercury vapor or something like that. Those were what we call gas discharge tubes. So if you did that with a gas, you sucked the glass tube out, you filled it up with a gas, and hydrogen was a particularly important one. And then you stuck a little electrode in each side of the glass, so you melted it just enough to stick a little electrode in there, and you put a high voltage across it. Lo and behold, it lit up. It made this cool glowing light. I don't know if you know this, but that's exactly what neon lights are. Neon lights are basically glass tubes that have been filled up with neon and other chemicals, actually. And then radiation, light will be produced when you generate a buttload of voltage across it. So it's got to be really, really high voltage to do it, 500 to 1,000 volts, that sort of thing. So when you do that with hydrogen, you get a very distinct yellowish looking color. Well, they discovered that if you took that light and ran it through a slit, so that way you had a nice crisp image of what the light coming from it looked like, and then you ran that through a prism, lo and behold, that yellow light became a series of lines. And that series of lines is called the hydrogen spectra. If you actually, you can Google it on your own, you'll see one in your textbook, of course, as well. But it's very distinct colors. And people didn't really understand why that was so. So that was one big experiment. Why are we getting these distinct colors? But they knew it was valuable because hydrogen had a distinct one. You do helium and it has an entirely different distinct one. You do nitrogen, it has a different one. You do water, it has a different one. Mercury. So all the chemicals and the elements had distinctly different light spectra. In other words, chosen colors that you'd see. It's really weird. It's like a rainbow, except you only have distinct lines of color. That's all you have. You have the whole rainbow is blacked out except for these distinct lines. And each element has a different series of lines, different distances between the lines, different colors, all that cool stuff. And remember, color for light is really either the wavelength or the frequency. Either one is acceptable to define the color because frequency times wavelength gives you the velocity, and velocity is always the speed of light. So you had all these distinct elements and distinct compounds giving very distinct spectra. Chemists knew this would be awesome because if they can ever take any material, heat it up like that, they can immediately find out what's in it by looking for the individual lines. So they knew it was super valuable. They didn't understand why. Everybody was trying to figure it out. There was even like a middle school teacher in Europe who had came up with a mathematical equation that gave you the actual wavelengths of the light that hydrogen produced, but he didn't really have any idea of how that came to be. Like he had no underlying theory. He just made a mathematical fit.
They use that to figure out what chemicals are on stars or in planets, right?
Exactly. Yeah, stars, planets, nebulae. You can even get it. That's basically some of the stuff that they'll use in chemistry labs as well. You just heat the things up and get their spectra. Yep. So that was a big problem. We had another problem too. There was this curve that basically, if you imagine taking, let's say, a horseshoe spike, so an iron rod, and you throw it in a fire. As the temperature got higher and higher and higher, it would eventually start to glow. In other words, prior to it glowing, i.e. us seeing it in the visible light, it was hot and it was emitting radiation, but that radiation was in the infrared, so we couldn't see it. We don't see infrared. By the way, snakes can, pit vipers, cottonmouths, copperheads, they can see it. And I think rattlesnakes can as well. But anyway, just to creep y'all out about when you're walking around at night. So anyways, this rod, if you stick it in the fire, it will heat up, and then it actually gets to a high enough temperature where it emits radiation in the visible spectrum. That visible spectrum starts just after the infrared, and therefore it's red. If you heat it up even more, and generally a backyard fire is not going to get it that hot, you could go on through orange, yellow. Our eyes aren't very good at seeing green, but you know the famous Roy G. Biv. Okay, so it'd go through all that. And if you actually watch like the old shuttle launches or rocket launches, you'll see when they first light it up, you'll see some reds, some oranges, and then it'll go almost transparent, translucent white. That's when it's gone beyond the visible spectrum into the ultraviolet. Most of the energy is going off and it's clear to smoke and all that good stuff. So it's emitting radiation then beyond the visible spectrum. And of course, it was going from red towards Roy G. Biv towards violet. So it went into the ultraviolet. So we all know that. We know that when you heat something up, it actually gives off radiation. And we know it also gives off a range of radiations. It doesn't just give, oh, I'm iron, I'm going to send out this perfect, 436 nanometer wavelength of light. It's not a laser. It actually gives off a whole distribution. So let me share my other camera with you for a second and show you what that graph looks like. So I am going to switch it to my document camera and show you what the graph actually looked like. So everybody knew what the graph looked like because they've done the experiment thousands of times. But basically, if you take energy released by the light as a function of, let's say wavelength. So this is low wavelength and this is high wavelength. Okay. It turns out this curve for all materials looks about the same. It goes up really rapidly, and then it reaches a peak, and then it gradually falls off slowly, slowly, slowly. Okay, so this side's supposed to be really steep. This side's supposed to be gradual. Let me draw it with a blue to make it look even more gradual. Okay, now this is called basically the Blackbody Spectrum, if you will. So if you heated something up and it was a perfect emitter and absorber of energy, it would look like one of these curves where it's got a really steep side and then a gradually falling side. And everybody knew that was what the graph was. There were equations that predicted exactly this behavior. There were equations that predicted this behavior, and there were even probably some equations that predicted this behavior, but none of those equations fit together. In other words, there was no single equation or explanation for why this curve was shaped the way it was. So that was another big problem of physics at the time. We just didn't know what was going on. Well, this one turns out to be the creator of quantum mechanics. This is where a guy by the name of Planck, drew an H there, Planck, P-L-A-N-C-K. Ooh, that's the worst writing I've ever seen in my life. Okay, Planck made the quantum hypothesis with this, and that was sort of the monumental creation paper for quantum mechanics. And it's kind of brilliant, but basically what Planck did was Planck imagined, like a lot of people thought at the time, that atoms existed. That's kind of odd. We didn't necessarily know definitively yet that atoms existed in the early 1900s. In fact, Einstein wrote a paper that could have won the Nobel Prize on Brownian motion that essentially proved the existence of atoms. He had like 7 papers that year, and every one of them could have won a Nobel Prize. But one of them was that, and that was the definitive proof of the existence of atoms. But everybody thought that, most people thought they existed, and then of course they would group up to make molecules. But in a particular metal, let's say like the iron rod, they expected the atoms to be adjacent to each other, connected by springs like this. And believe it or not, like I used to work in structural engineering, and when we design, and I didn't actually design skyscrapers, but when you design a skyscraper, you sort of treat the skyscraper as if it's a bunch of atoms connected by springs like this. And of course, it's 3 dimensions, so there's springs back here going to adjacent atoms, and there's springs back here going to adjacent atoms, and those are connected like that. And those are connected to another line of atoms, so on and so forth. So that's sort of the way you treated a metal. And then you say, okay, well, these atoms have to actually vibrate. They're going to vibrate back and forth closer and closer to each other by the spring vibrations, okay? And what you think when heat or energy is applied to these metals is, you know, that from what we know call kinetic theory and thermodynamics, we know that atoms or molecules speed up in their vibration when you give them energy. So that makes these distances shrink and stuff like that. So Planck had the idea of, I'm going to pretend like these frequencies at which these atoms vibrate were not just a continuous number. Like your speedometer gives you a continuous number if you have the old analog one, which is just a bar that goes back and forth like this. If you have a digital speedometer, it doesn't give you a continuous. It only gives you the whole numbers, right? So what he was doing was a common mathematical trick of the time, which was, hey, let's take this variable, in this case it happened to be frequency, that really could be any number between 0 and infinity, and let's pretend it's certain select numbers like 0, 1, 2, 3, okay? So he said, let's let the energy of these particular photons, because he's pretending the light is a particle again, like Newton had said, let's pretend these energies actually can only be n times some constant, which we now call Planck's constant, times the frequency. And this n had to be a 0, a 1, a 2, a 3, ... Okay? It couldn't be anything else. Now, the deal is, what you do when you're making this kind of approximation in mathematics is you work out as much math as you can to get through all the hard parts, because a discrete variable like this, one that only has certain values, is a little easier to deal with mathematically than a continuous variable. You can do sums and stuff like that as opposed to integrals, and sometimes that makes life a little bit easier. So at the end, you're supposed to let this number go down to 0, and then that would cause the adjacent ones to have zero distance between them. So you go from the separation being 1 HF or 2 HF or 3 HF, you go to the separation going to 0. And then you'd have your continuous variable back. Well, it always looked promising until he took that last step. So he said, the heck with it. I'm not going to take that last step. I don't know why it worked, but it did. So he publishes his paper saying basically that light is made up of particles, and these particles are being emitted by the vibrations of these atoms or molecules, and they're only allowed certain discrete frequencies, 1 times some constant times F, 2 times that same constant times F, or 3 times that same constant times F, and so on and so forth. When he did that, he got an equation that matched this perfectly. Okay, it was a monumental discovery. He won the Nobel Prize for it. It was crazy. No one understood why, but that gave us quantum mechanics. So that was kind of cool. Well, Einstein comes along and says, well, this is brilliant. He thinks he can explain some other experiment that's going on, which basically says, hey, if you shine light on a metal, that metal will all of a sudden generate a current. And when you think of light as a wave, there is an actual way to explain that happening. You sort of picture the light as a wave, and it causes the individual atoms to shake so hard that like an electron falls off, and then that electron will go to a positive area, and that's a current, right? So that is a way of explaining it, but it turns out when you actually do experiments to try to measure things like the delay and how long it takes, and whether it depends on the frequency or whether it depends on the intensity or the brightness of the light, all those things did not match what happened in reality with regards to light hitting a metal. So Einstein used this and explained this effect, which is called the photoelectric effect. So Einstein used that to explain the photoelectric effect. So, and he said, hey, look, if I'm right, then what you should be able to do is do this nice little graph, and this nice little graph is going to be a straight line, and that value is going to give you an important parameter about the metal that you're using, and this line, this slope and stuff has a very specific meaning. And if you get that graph, I'll be right. And immediately they got that graph, and Einstein won the Nobel Prize. Again, this was that 1905 where he had such a banner year. So he won the Nobel Prize for that. So Einstein's one of the second people to write a fundamental paper that created quantum mechanics, even though he literally on his deathbed was trying to prove it was wrong. His last notes, literally the notes he had in his hand when he died in his bed, was him still trying to find a way to get rid of quantum mechanics. So he did not adopt it totally, but he did contribute to it, and in fact won a Nobel Prize for it. Most people thought he won it for relativity, which was also that 1905 a publication of that 1905 year. So he didn't win the Nobel Prize for special relativity, even though it was published in 1905, and it certainly warranted it. But he won it for the photoelectric effect. He didn't win it for the Brownian motion either, but it was pretty banner. So those are two fundamental ideas that came up to create quantum mechanics. And I'm trying to get to light now. So remember that last experiment that we haven't discussed, which was the one about the discharge tubes, the glass tubes that you fill with gas. Well, Niels Bohr comes along, and Niels Bohr says, hey, this guy Planck is saying light is a wave. And in physics, we study waves all the time. That's all we study. It's a huge fraction of what we study anyways. So and not only that, we relate them to masses on springs because they give you the same shape as a mass on a spring oscillating. So Bohr said, hey, I know about waves, so I think I might be able to attack this gas discharge tube problem with this idea of light being a wave. So his idea was this. He said, we have an atom. And at this point, we actually had the idea that the atom was like in the planetary model. So in other words, for some time, there was this model called the Plum pudding model. And it's Great Britain we're talking about here. So, everything means something different. So if someone asks you if you want a biscuit, you're like, why would I want a biscuit? Well, that means a cookie. Okay, so in Great Britain, it's a cookie. Same thing with a pudding. A plum pudding is not a pudding. It turns out it's like a bread. So a plum pudding would be like raisin bread, where you use plums instead of raisins. So the plum pudding model of the atom was, hey, we found these particles that exist in nature, and they seem to make up atoms, i.e., protons and electrons, and we think those things are just dispersed through a lump of material, just like plums disperse through a lump of bread. Okay, so that was the model. Well, this guy by the name of Rutherford, who's really this brash scientist, he said, "Science is physics, the rest is stamp collecting," which I like to use when I talk to my chemist friends and my geology friends and my biology friends and stuff like that. But just out of joking, because I love all the sciences actually. But anyways, he did this neat experiment where he fired alpha particles, which is the helium nucleus. They didn't know that at the time, but that's what it is. It's basically 2 protons and 2 neutrons. And a proton is well over 1,000 times heavier than an electron. It's like 1,200 times heavier than an electron. And same thing with a neutron. So imagine 4,000 times the mass of an electron hitting individual electrons in a plum pudding. That was his plan. He wanted to see how the electrons and stuff were dispersed through the plum pudding. So he decides to take a little piece of foil. And, you know, if you're in science, why would you waste your time on using aluminum foil when you can buy some really fancy gold foil? So he used gold foil, and gold, we actually did use that for a good reason. Gold was one of the biggest atoms they knew of at the time. They knew it was going to be massive and heavy. So he shot these alpha particles at the gold foil, and he expected, you know, a little deviation here, a little deviation here, some would go straight through, and that's about it, because really this thing's huge. And I'm going to use a horrible analogy here because I think it might wake you guys up. It's like a Mack truck running through a playground. Even if he's a conscientious dude trying not to hurt kids, he's still going to have to, you know, dodge quite a bit. So he'll come out and make little deflections. Where if it's a Mack truck running through a ground full of those big earth-moving trucks that are like, you know, 40 foot tall, then obviously they get butted all around and stuff. So these things interacting with small things are just going to cause small deviations like that. That's what he expected. And according to Rutherford, he was being a good scientist, but some people in his lab suggested that they actually just left the detector in the wrong spot and it went off. But anyway, what happened was a detector ended up being over here, and these detectors normally look like, they draw them like this, like they're a little can. So we had all these detectors out here, so he could mathematically tell exactly where these things are going and then work out backwards to figure out exactly what the orientation or what the positions of the various particles are within the plum pudding. But all of a sudden, one of these went back here. That's an amazing thing, because remember, they're thinking in here is itty bitty things, and here is this massive, massive thing, and you shot it in and it bounced backwards. He said it was as if you fired a 16-inch cannon. So we're talking, you know, World War I era, where we had guns who fired more or less bullets that were 16 inches in diameter. If you fired one of those at a bowling ball and it bounced back at you, in other words, the bowling ball stayed its ground, but the 16-inch cannon shot right back at you, you'd be pretty stunned. And that's what happened. That's what Rutherford said. It was like a 16-inch cannon was shot at a bowling ball, and the 16-inch cannon round came back at you. So that made us completely rethink the model of the atom. We ended up coming up with what you've probably seen in old footage, the planetary model, which is unlike our planets, which are all basically in one plane. You imagine the electrons as if they're orbiting in various planes around a dense thing called the nucleus. Okay, well, that's all well and good. And it had fit the data, because obviously there's something in here supermassive. We did find out, in fact, it was the nucleus of the gold atom, which is huge. So yeah, there is a super massive thing. We'll later learn that it's really, really small, though. In fact, it's about 1/10,000th. The radius of this is about 1/10,000th of the radius of the orbits. So literally, if you had a nucleus blown up to the size of a grape seed and you put it in a 50-yard line of a football stadium, let's say my favorite team is Washington. If you put, yeah, it's sad, but we still love them. So anyways, you put a grape seed at the 50-yard line in Washington's stadium, the actual orbit of the electron would be out in the parking lot. So that gives you an idea how small the nucleus is compared to the atom. So now that we have this model, in comes Bohr. Bohr says, well, we've got a problem because the laws of electricity and magnetism, which were created by a guy by the name of Maxwell, James Clerk Maxwell, he's a sad story. He died at like 48 or something like that of a horrible case of stomach cancer and without the respect of his peers, even though he did hold the Lucasian Professor of Mathematics chair, which is the same spot that Newton held and the same one that Stephen Hawking held until he died as well. But anyways, he was a brilliant scientist, but he came up with the laws of electricity and magnetism that a lot of people just didn't get, and therefore they didn't really think he was that good of a scientist. But anyways, he had these laws of physics. By now, we knew they were right on. They were exactly correct. And basically, the Maxwell's equations say that if you have a charged particle, like an electron, which is, a negatively charged particle, if you have a charged particle going in a circle, that means it's accelerating. Remember, anytime the velocity changes, the object's accelerating, and the velocity can change by changing direction or changing speed. So even if they're going in perfectly circular orbits, so their speed's always the same, they're still accelerating because they're changing direction. Well, whenever you have an electron that's accelerating, Maxwell's equations say that they're going to give off energy. They're going to radiate radiation out, okay? Well, if that's the case, then the only way an electron can lose energy is by slowing down. Well, if it slows down, then the pull, the attractive pull of the positive protons pulling on the negative electrons is going to cause the electron to get closer and closer and closer until it literally will come in, and they calculated that the atom would last like a millionth of a second. So even hydrogen, the atom, and I can't even remember if it's a millionth or a billionth of a second, but hydrogen will not last very long, and we know hydrogen is the most prevalent element in the universe. So that certainly wasn't acceptable. So Maxwell had another idea given Planck's hypothesis. So, or excuse me, Maxwell. Bohr had another idea having learned about Planck's hypothesis. He said, what if, just like light being a wave, what if electrons behave like waves around the nucleus? So here's the nucleus, and then there's an electron orbit. And we know for a fact that electrons making orbits produce radiation according to Maxwell's equations, and the only way we could make any sense of it not is if we came up with a new idea about physics, and that's what Bohr did. Bohr said, well, maybe Maxwell's equations don't apply in certain instances. Maybe the electrons act like a wave. If the electrons act like a wave, then there's certain allowed waves. So for instance, if you pluck a guitar string, it can vibrate like this, or if you pluck it a little more forcefully, it can vibrate like that. If you pluck it a little more forcefully still, it can vibrate like that. Y'all know what I'm talking about? If y'all done that with a spring or a jump rope or something, you can wiggle it back and forth and it'll get all these different shapes. And that's what waves on strings do. So if an electron is acting like a wave, then maybe the orbits that are allowed, the ones that wouldn't radiate, like Maxwell said, are only ones whose distance around is 1 wavelength, or 2 wavelengths, or 3 wavelengths. So let's take this third one, for instance. Let's say it's 3 wavelengths. Then that would mean a wavelength normally is represented by a center line, a peak, a center line, a trough, a center line. Okay, so that'd be like 1 wavelength. So if I tried to imagine that, I would say, okay, well, here's the electron 1 wavelength. Here's the electron 2 wavelengths. Here's the electron 3 wavelengths. So if this distance around here was 3 wavelengths, and the symbol we use for wavelength is lambda, it's that little Greek letter. If we allowed that to happen, then this one would have to be 2 wavelengths, this one would have to be 1 wavelength, this one out here would be 4 wavelengths, so on and so forth. And that was just Bohr's guess. Maybe when electrons are actually acting like like waves, maybe they're allowed to be in orbits without giving off radiation, but those orbits have to be special ones whose distance around is multiple of a wavelength. So these were half 2 halves, 3 halves, 4 halves. These are all 1, 2, 3, 4, not halves at all. So when he did that, he actually came up with exactly that same formula that the middle school teacher did for the spectra of hydrogen. In other words, he was able to predict using the laws of physics, actually the laws of electricity and magnetism, because we had to use Coulomb's equation, and the E equals HF, where you can only have 1 HF or 2 HF or 3 HF. Putting all that together, he was able to explain each of the little colors that the hydrogen atom put off. And not only that, he predicted ones that we didn't see because they were in the non-visible part of the spectrum. And it was actually right, believe it or not. Eventually, when we looked there and looked outside of the visible spectrum, we found those were correct. So it was really cool. Bohr had, by making his model of the atom where there's a nucleus and certain allowed orbits, had explained it. And the way he explained it is this: hey, whatever energy this orbit has, let's call it E3, that's the energy of the third orbit, and it refers basically to the fact that the distance around the orbit is 3 wavelengths of the hydrogen, of the electron. And this one would be, say, E2. And then if an electron is going to fall from here to here, that electron goes from high energy, just like you have a lot of energy if you're on top of a telephone pole. Remember, energy is like something that gives you the ability to do work, and work you can think of as the ability to drive a nail. Okay, you can think of it as being a really small nail going through styrofoam, or you can think of it a really big nail going through, steel. It doesn't matter, as long as you're thinking of some case in which a nail is driven, you're thinking of something that's doing work on it, and the ability to do work is energy. So if you're up on top of a telephone pole, you could certainly fall from that telephone pole on a nail and drive it into the ground. Ergo, you have a lot of energy here because that energy just allowed you to do work driving the nail. And being lower, let's say you're at the halfway up, you could probably drive that nail about half as far. Okay, not really the way the math works, but we'll just leave it at that. So his idea was the energy in the third orbit is higher than the energy in the second orbit. So if an electron fell from here to here, it had to get rid of that energy. Energy is conserved. So it would do so by spitting out a photon. Okay, so this is a photon of light. That's the particle. That's the corpuscles that Newton was referring to. And the energy of that photon would equal E3 minus E2. Okay, the energy that it had there minus the energy it has there, that's the difference in energy between these two orbits. So that's the energy the photon would have. And if you set that equal to h times f, it would give you a specific frequency. And lo and behold, that frequency would correspond to a specific color that we saw in that gas tube. Isn't that cool? He completely made it up. It's like there's no reason to think that an electron is a wave. There's no reason to think that photons have a discrete amount of energy, HF or 2HF or 3HF, yet they predicted it just on a whim, and lo and behold, it worked out. That was crazy. So this turns out to be the big deal. The difference in energy from one orbit to the next is when you set it equal to HF, you can solve for F, and that frequency will be representative of a color you'll see in those tubes. So when you do that to hydrogen, you get all the colors that people had seen, plus colors that no one had seen before that happen to exist outside the visible spectrum. That was the Bohr hypothesis, and that's what he won the Nobel Prize for. His son later won a Nobel Prize as well. Bohr's an awesome dude. He's like 6'5". He was a professional soccer and rugby player. He was nobility. He made beer. He was like the life of the party. Everybody. He's sort of like the perfect Biff, but without all the negative aspects of someone named Biff. He's like just the coolest guy around. So it's kind of awesome to think that we had this Nobel Prize winning physicist that wasn't quite the geek that a lot of them seem to be. Even Einstein wasn't that much of a geek. Women tended to gravitate towards him, and I'm not saying that's the only indicator, but he was quite a personality. In other words, people enjoyed talking to him. And then other ones were more geeky, like Dirac was sort of a Sheldon-esque character, as in Sheldon from The Big Bang Theory. But anyways, that is the big thing about astrophysics that we needed. We needed to understand, where does light emanated from a hot object come from, and why do we get the colors that we get? Well, we get the colors that we get because these numbers here, these energies for here and here and here, are dictated by very certain parameters. In fact, it turns out the energy levels really only depends on the number of protons in the nucleus. So if you have one proton, you have a very specific set of orbitals that are allowed. That's the hydrogen atom. If you have two protons, that turns out to be helium. No matter how many neutrons you have, helium has two protons. That's what makes it helium. So when you have two protons, you have helium, and that has an entirely different set of wavelengths. It's like fingerprints for atoms. So the number of protons produces a distinct set of orbital energies that are allowed, and those orbital energies that are allowed are as unique as we can tell, is more unique even than fingerprints. You know, there's not a really good science saying that fingerprints are really unique from one person to the next, but we keep running on it because we, you know, very seldom do we find two people that have nearly identical ones, so it works okay. In the case of atoms, we don't know of any that have the identical orbitals. So this energy separation is unique to every atom. So if you get all the different ways, an electron falling from there to there, or an electron falling from here to here, or from here to here, or from here to here, or from here to here, all these different things give different energies and different colors. So each one of those represents a color, and the group of them tells you, hey, this is a certain element. So that is the astrophysics that we needed. That's how we can now take light from a star or a gas or you know, a nebulous cloud, for instance, and tell what elements are present. And that's all because of, obviously, you saw Maxwell was used. You saw that Planck worked with basic kinetic theory and came up with the quantum hypothesis. And then Einstein used that to explain the photoelectric effect, which is another aspect that actually, that was the aspect that sort of suggested that the electrons jumping around could be related to energies of photons. And then Bohr comes along and uses the work of Maxwell and others, Planck, for instance, and comes up with the model of the atom, for which he won the Nobel Prize. And then he immediately takes that exact same model and works it out for helium, and it's an abysmal failure. It's kind of a shame, but he thought that was going to be the plan. But it's kind of neat because it made us think that electrons had wave-like properties. That was amazing, and we needed that because if we don't have wave-like properties, we don't get a wave equation for quantum mechanics. And without a wave equation for quantum mechanics, we don't understand quantum mechanics any further. So it's almost like, you know, God gave you a little stool so you can look up over the edge, but you can only see a little bit of what's on the bar because you're not tall enough to see everything. So you saw this little bit that worked, and it gave you an idea to think about waves. And then later we were able to use that idea of waves to come up with a wave equation that ultimately allowed us to explain how atoms and light and matter all interact. So,
question.
Yes, sir.
So is this topic, like about light and all this stuff, going to be on test 2 or test 3?
This would be more like test 3.
Okay, gotcha.
And you'll see when you start taking the practice test, you'll see where those questions come in. There are some overlap, but in 3 and 4, they do a little bit of overlapping with 5 and 6. So you'll see some stuff that sounds familiar to this, but most of it's in test 3.
Okay.
Okay. So if we keep going on with this, it turns out that light can interact with matter in a couple different ways. So here's a nucleus, here's an orbit, here's an orbit, and here's an orbit. And this light particle, which we normally draw as a little wave with a circle, okay? This light particle comes up here. The atom looks at it and says, hey, what's your frequency? Or better yet, what's your energy, okay? If it gives you the frequency, then we have to use E equals HF. Or if it gives you the wavelength, you can use the fact that the velocity of light is c, the speed of light. You could also use E equals hc over lambda. Either one of those would be acceptable. So this atom sort of asks the photon, hey, what's your frequency, or what's your wavelength, or even simpler, what's your energy? And then the photon says, well, this is my energy. And then the atom quickly looks, well, how much energy does it take for an electron to go from this orbit to this orbit? Does that match this one? No. Okay, what about from this orbit to this orbit? Does that match it? No. And you keep on going through all the different orbits and all the different ways that they can make a transition from one low orbit to another higher orbit. And if he finds out none of those energies match, then the photon just goes on. No matches. Okay, so if the energy doesn't match at all, the photon is not bothered whatsoever by the atom. The atom and the photon do not interact at all. Now, in another case, as you might suspect, this is a different element, and now a photon comes along. And the atom says, hey, what's your energy? And this energy this time matches. So all of a sudden, this electron will jump from this orbit to this orbit, and the photon will disappear. Instantaneously, the photon disappears. It jumps up, it makes a quantum leap. Okay, that's where, you know, the term quantum leap came from. It literally instantaneously, the electron disappears here and appears there. And it could be for any transition from one orbit to the next. So that's cool. That's actually what happens. This is matter interacting with light. So the photon disappears at the same instance that the electron jumps up. Now, there is a little allowance for energy to be non-conserved. There's this neat uncertainty principle that says the difference in the energy, the difference in time, is greater than or equal to h bar over 2, which the h bar is the same constant we know of over here, Planck's constant, only it's divided by 2 pi. So there, you actually can allow an uncertainty in energy. In other words, energy could be conserved long as it's not, could be non-conserved long as it's not done for a very long period of time. That's just a sidebar, but I usually just use the phrase instantaneously the photon disappears, and instantaneously the electron disappears here and appears there. Okay, so that is one interaction with light, and this is that was the second one. Now the third one is I have an excited atom, if you will. So in other words, the atom has an electron that's higher than it could be. There's an open spot right here. Okay. Oh, drops paper. Okay. There's an open spot right here. In other words, this orbital allows another electron more than it has, and there's an electron up here. So obviously, just like you being left on top of a telephone pole, you don't want to stay up there, right? You could fall at any instant. You could land on a nail and drive it in the ground and prove Mr. Younger right, and that would be horrible. So you want to get down. Well, the same thing with the electrons. When they're in an excited state, in other words, the atom's excited, then the electron wants to fall down. So what's going to happen now, especially if it's the same one that happened up here, so if it's the exact same atom, then it's obviously eventually going to fall back down, boom, and instantaneously an electron is created. Okay? This electron will have an energy equal to E3 minus E2. Just like this one had an energy E equals E3 minus E2. Okay? This photon that was absorbed had an energy E3, the third level, minus E2, the second level. So it was absorbed. Now this one, all of a sudden, an electron drops down, and instantaneously a photon is created whose energy is E3 minus E2, and it's actually going off in a random direction. That's kind of important because that helps us with Kirchoff's laws. So the three ways that light can interact with matter is if the energy doesn't match a difference in orbitals for an electron, they don't interact. The electron just keeps on going. Or excuse me, the photon just keeps on going. If the energy matches, then the photon will spontaneously disappear and the electron will jump up to an energy whose allows the change of E3 minus E2. And then the third way is basically matter can create energy. It can create a photon. Matter can create light because this electron, if it happened to have been boosted up to a higher level than it needs to be, it's not going to be comfortable there. It's not going to be there for very long, so it will eventually fall down. When it falls down, it'll create a photon whose energy is equal to E3 minus E2, and that photon will come out in any random direction. So that is how light interacts with matter, and that leads us to the last part that I really wanted to discuss. That's sort of the complicated stuff, and that's Kirchoff's laws. So Kirchoff, if you've had anything with electricity and magnetism, you know about Kirchoff's laws of electricity and magnetism. Is the same dude. Like I said, these people in these times, these scientists were brilliant, and they were usually brilliant in several fields. So sure enough, this guy Kirchoff comes up with this idea. He basically says, hey, if you have a light bulb, which is a hot incandescent source, i.e. The actual hot incandescent part is the filament that's been heated up. That metal is a hot incandescent source. Incandescent, you can sort of think of it as basically producing light. Specifically, in most cases, we said incandescent light is a light that we can see the light from, but in principle, you could give off light beyond the visible spectrum. So Kirchoff said, if you have a hot incandescent source, like a wire that's been heated up by a current running through it, then you will get a very specific spectrum. It's that blackbody spectrum that Planck predicted and explained. So that's a blackbody spectrum. It's a blackbody spectrum. You could also call it a rainbow, because it really is literally all the colors. You remember, this is a graph of wavelength versus energy given off, and this shows basically every wavelength is a possibility. There's no wavelength that's not represented here, so you get all the wavelengths, including Roy G. Biv, which would be some small part in here. Roy G. Biv, red, is actually a long wavelength, so we actually have to write it backwards, Viv-Gior. So maybe Viv-Gior is right here, right? So this way is infrared, or excuse me, this way is ultraviolet, and this way is infrared, okay? So that's one spectrum you get. Now, if you take that hot incandescent source, okay, and you put it behind a cool, lower density gas, then what's going to happen is all the light that comes through here, it's going to act like that atom that we showed you a second ago. All the atoms in there are going to evaluate every photon coming through the gas. So each of these photons coming from this, which means every color possible, each of the photons coming from this will be evaluated one by every atom and molecule in here. And if a photon can be absorbed by an atom or a molecule that's in here, then it will be absorbed. And then all that's left is the rest of the rainbow. So you basically are going to have a rainbow with spots missing. And instead of getting Planck's graph or the blackbody spectra, you'll get something that looks like this. Like that, okay? So what's happened is this is supposed to be the same curve as that, okay? Because I used the same source. So this is supposed to be the same curve as this, but what's happened is instead of us having that complete blackbody spectrum that would go like this, okay, we've got missing spots, missing wavelengths in there. So if we looked at it, we looked at this one up here would be a rainbow. If we looked at this one down here, it would be a rainbow, but there would be missing spots. So it'd have a line here missing, a line here, a line here, a line there, a line there, a line there, a line there, maybe. All sorts of weird patterns, okay? So this one's called an absorption spectra or a dark line spectra. Okay, so that's what I mean by putting spectra up top here. So when you have a hot, dense source behind a cool, lower density source, then you get an absorption spectra, which is basically a rainbow with missing spots. Now we got another scenario. What if we have a hot incandescent source like we did before, only this time the hot incandescent source is not in our line of sight. Okay, so our line of sight is this way. Actually, let me put it this way. Our line of sight is this way. This is a cool, lower density. It's hard to write on a piece of paper that's bouncing up and down. It's a cool, lower density gas. See, we don't get to see the light directly from the hot incandescent source. All we see is this gas, and this gas still has all this whole rainbow of frequencies hitting it. So all these atoms in here that can be excited will be excited. All these molecules that are in here that can be excited will be excited. They will have electrons in a higher orbit than they're supposed to be. So little by little over time, they will do what this one did, which is the electrons are going to fall off and shoot, are going to fall down and shoot out photons, create photons. The photons aren't stored inside the atom. They just are created all of a sudden. But the electrons will fall down and create photons that will fire off in random directions, some fraction of which is us. So what we get in this case is what we call a bright line or emission spectra. And in fact, I'm trying to make it look like there's a peak everywhere there's a trough in this one. Okay, so obviously I'm not going to do it that well. But it's going to go across like here. And here. And then here. And some here. And some little ones here. So on and so forth. So again, this is supposed to be the same curve as before. Okay, but if you laid this one on top of this one, it would make the complete rainbow that is this one. That's the key point. If this was the same gas and the same hot incandescent source, that's what would happen. This one's called a emission spectra or a bright line spectra. Okay, and as far as the rainbow goes, it would be a bright line, and everything else would be black. So when we're looking at it, it would look like this. All black, all black, all black, all black. Except for those distinct lines. Okay? So that's Kirchoff's laws. It basically says a hot incandescent source will produce a continuous spectra. That's another word for it, continuous. I knew I was trying to come up with another one. I couldn't remember what it was. A continuous spectra, a blackbody spectrum, or what we call a rainbow. Okay? If you put that hot incandescent source behind a cool lower density gas, then you'll get basically the rainbow, but with colors missing. That's the absorption or dark line spectrum. And if you're just looking at the cool low density gas without the hot incandescent source behind it, then you get just the lines that were dark are going to appear down here as bright lines, and everything else will be black. So that is the essence of how these waves interact with matter, and how this light interacts with matter, and that's how we know so much about stars. So the depths, for instance, of these pits are the heights of these spikes right here. They are in some sense directly related to the amount of a quantity. So for instance, this little spike right here, let's say that belongs to titanium oxide. Well, the fact that it's really small says titanium oxide is a very rare thing in there, whereas say this one's a hydrogen line, well, there's a buttload of hydrogen. Okay, so they can actually not only tell what elements are present, they can tell in what percentages. And that's how we've learned so much about what stars are made of, what nebula clouds are made of, what the clouds that would precede the creation of our planet or of another type of planet like ours, what they are made of. And in fact, when we look at our sun, we get this type of spectra, an absorption spectra. And that's kind of amazing because that alone, just knowing that we get this rainbow spectra with missing colors tells us something about the sun already. It says that the sun has a cool, lower density gas around something hot and dense. We now know that that hot, dense thing is the core of the sun where nuclear fusion that is, not fission, nuclear fusion takes place. And then the photosphere, which is a very thin layer around the outside, is the cooler, lower density gas that's absorbing it. And that cool, low density gas is made up of the very elements that would have existed in our nebular cloud before our planet was formed. So when we look in the solar system, we find out that, or we should find out that basically those same elements that are in our sun should be roughly in the same percentages in all the matter that we find that hasn't been changed. So that's why we look at comets and asteroids and see what their composition is. And if that composition does indeed match the sun, then we're more and more confident that that is what our nebular cloud was made of before we created before our planet was created. Isn't that cool? So any questions on that part? I'm going to go for about a couple more minutes, but I'm going to share the screen so we can go over these slides to make a little bit more sense to you guys. So let's do this one right here. That's not really the one I want. No, this one. Yeah. Okay, so I'm going here. So this asks what is light, and what I'm telling you, these are your learning goals. They're not exactly what we put on your Moodle page, but they're very closely related. You can see you want to be able to describe the wave and particle properties of light, describe the electromagnetic spectrum. That I'm going to give you some ideas for. You'll read it from your book, but basically there's a wonderful mnemonic. I'll say it. You can watch this later and get it, but I'll say it kind of slow in case y'all want to write it down. I made up this mnemonic because I'm a big Rush Limbaugh fan. I listen to him quite a lot. I shouldn't say fan. I enjoy his program, and I've listened to it or watched it on TV since 1989, if that tells you anything. But he's always talking about how us teachers are commies or communist people. So I made up a cool little mnemonic for the electromagnetic spectrum based on that idea. And it is, y'all ready to write? It's great excess, and you spell the excess as not how it's supposed to be spelled, but just X hyphen CESS. So great excess undermines various industries. You normally end this with a comma. Marxism rules. So great excess undermines various industries, Marxism rules. Great excess undermines various industries, Marxism rules. Great excess undermines various industries, Marxism rules. Again, I don't believe any of that crap. I just thought it was funny to make use of the fact that he always says teachers are commies, so that's kind of fun. And you'll see in a second when I go over the electromagnetic spectrum, you'll see what I'm talking about. Great is for gamma. I'll walk you through that. So the big question was, what is light? Well, it turns out light has a finite speed. Your book talks about when we first measured it, it's about 300 million meters per second. That's the figure I use. Some books use the kilometer per second figure. This book uses the kilometer per second figure, and I don't really care that much for it. I usually just use the meters per second because that allows me to not have to make my students convert units so that they can use the wave equation. The wave equation is one of the few equations I make my students use. But one of the first times we really made a good attempt at measuring the speed of light was when Romer did it. And Romer did it by looking basically at the lag time from light coming from moons of Jupiter. And with that, we got some really cool results. But just remember the figure is 300 million. That's 3 followed by 8 zeros. And that's the speed of light in meters per second. If you want to know a more reasonable figure in terms of units that you're used to, it's 186,000 miles per second. 186,000 miles per second. That's so fast that it takes about 1.2 seconds to get to the moon. Whereas it took, Apollo astronauts several days. I think it was actually on the order of weeks to get there. So the speed of light is really, really fast. It could go around our equator about 8 times in a single second. So yeah, the speed of light super, super fast. That's why no one ever noticed it before, but it is fast, and but it is finite, and that makes a big difference because, as you know, when we look to the stars, we are in fact looking into the past, because even the nearest star other than our sun is 4.3 light years away. So we're seeing it as the light that left it 4.3 years ago. This is what Maxwell taught us light was. It's an electric field. Notice these are, let's say, vertical. So it's oscillating vertically. And then perpendicular to that is a magnetic field, or oscillating left and right, say. And then perpendicular to both of those is the direction that the wave is traveling. That's what Maxwell's equations taught us. So we knew light was a wave, which was kind of a problem because, we had all of Newton's equations and they were all done as if it's a particle. But then later on, we had Huygens and all these other guys, Fresnel, that treated light as a wave, and they got the same equations. So we really didn't know what was going on. And then the quantum thing comes along and we had to describe it as something else. So these are the parts of a typical wave. Remember I said a wave, most people draw it as the midline up to a peak, midline again, down to a trough, midline again. That would be one wavelength. But that's also the same as going from one peak to one peak, or from one trough to one trough. That's the wavelength. It's something we normally measure in meters, miles, kilometers. In my class, I do predominantly meters, okay? The amplitude turns out to not be very relevant in most of physics, but definitely not in astronomy. And that's just the distance from the midline to the peak, or the distance from the midline to the trough, vertically, perpendicular to the way it's traveling. Surfers often will be like down here and they look up at the top of a wave and they say, wow, that's a 10-foot tall wave. In physics, we'd call that a 5-foot wave because the amplitude's only 5 feet, even though you're seeing 10 foot of water coming at you. It's kind of scary, right? So that's how amplitude's related to wave height. Then there's another parameter called the period. So if you're standing on a pier right here and this wave passes you by, you start timing it the instant this peak gets to you, and then this peak moves to you, moves to you, moves to you, and then you stop the timer. The time taken for the wave to get from here to here is called the period of the wave. That would be measured in seconds. If I found out that the period of a wave is, say, 4 seconds, then there's another thing you can talk about called the frequency. And I'd ask you, the period of a wave is 4 seconds, and I ask you, how many waves pass you by in a single second? What would you say? Does a whole wave make it past you in a single second?
Sorry, could you repeat the question?
Yes. If I tell you that the period of a wave is 4 seconds, that means it takes 4 seconds for a whole wave to pass you by. How many waves pass you by in a single second?
It'd be less than 1.
It would be less than 1. Can you think of a fraction that it might be?
A quarter.
A quarter, yes, 1/4. And that's not a coincidence. It turns out the formula is that frequency is equal to 1 over period. So the F I use for frequency and the capital T I use for period. F is equal to 1 over T, or T is equal to 1 over F. Either way you slice it, works out. When you realize that the wave moves one wavelength in one period, you can then say, oh, well, I know from my speedometer that speed is miles per hour, and miles is a unit of anybody? Distance, exactly. And hours is a unit of
time.
And per in mathematics means divide. So you divide the distance by the time and you get the velocity. So the velocity of the wave would be the distance it traveled divided by the time taken. We already know from the definition of the period, the velocity, or the wave, actually travels a distance of one wavelength in one period of time. So velocity is equal to wavelength over time. And you'll see the equation again in a second. It's actually going to be in the book. So we now have an equation: velocity equals wavelength over time. But 1 over time is the same thing as frequency. So you can say velocity equals wavelength times frequency. So that's ultimately the equation we're going to use. I'll show you that in a second. This is the electromagnetic spectrum I was telling you about. the visible part is the Roy G. Biv. Notice in this order it's Vibgyor. So Roy G, G for green, Biv, there's blue in there somewhere, and then there's violet. So notice it goes great excess undermines various industries, Marxism rules. So great is for Bill Bixby, our Incredible Hulk. Anybody know the reference? Bill Bixby became, or is that the actor or the character? I can't remember. Anyways, he became the Incredible Hulk because he's exposed to gamma rays. So G is for gamma rays. X is for something when you get a broken bone.
X-rays.
An X-ray. Your suntan and people's skin cancer comes from the U.
UV rays.
Yeah, UV, which is ultraviolet. The V is what we can see, so we call it visible. And then the I keeps our French fries warm while we're waiting in the line at Burger King.
Infrared.
Infrared. Basically a light, but the infrared's keeping it warm. And Hot Pockets is the M.
Microwave.
Microwave. And then R is for radio waves, which a lot of people think are sound waves, but they're not. They're actually they're electromagnetic waves. All of these types of radiation travel at the speed of light. They all travel at the same speed, c, 300 million meters per second. So this is in order of, notice the wavelength's really, really small here. So this is an order of large, small wavelength to large wavelength. So that's a question I often ask my students. List the parts of the electromagnetic spectrum in increasing wavelength. And you'd say great excess undermines various industries, Marxism rules. If I said list the parts of the electromagnetic spectrum in order of increasing frequency, you'd have to go the other way. Because frequency, since velocity is equal to frequency times wavelength, and the velocity is always the same. When frequency goes up, velocity or wavelength has to go down. So
yeah,
that's why
inversely
frequency
proportional.
goes down. Go ahead.
I said inversely proportional, yeah.
Exactly, yeah, they're inversely proportional. And of course, the visible spectrum, I do expect you to know that roughly the visible spectrum is from 350, say 400 nanometers to 7 or 750 nanometers would be acceptable. Some books use 400 to 700, some books use 350 to 750, some use 400 to 750, all sorts of stuff. But roughly 400 to 700 nanometers is the length of the wavelength of visible light. And remember, a nanometer is if you took the height of a doorknob and divided in 1 billion equal parts, that would be a nanometer.
Quick question.
Yes.
So the frequency, so neither the frequency nor the wavelength actually has an effect on the speed of light?
They do in some sense. Basically, when light goes from air, it has essentially the speed that it has in a vacuum, which is 300 millimeters per second. But when it goes into glass, its speed slows down by a factor of 1.5, and that's done by the wavelength or the frequency changing in such a way that it gets that. That's called what we call the dispersion relation. But the two always multiply to give the speed of light in that material. So whatever your frequency is and your wavelength, if you multiply those two numbers, you will get the speed of light for that material.
Okay.
Okay. Gotcha. Neat experiment you guys can try. Disable the rotisserie mechanism in your microwave, you know, the little plate that spins around. If you turn that upside down, it usually will not let the device turn it around anymore. So it'll just sit still. And then you take a Hershey's chocolate bar and lay it on a plate, on that plate, and heat it until you start seeing little lines in the Hershey bar melt. Those lines are basically where the peaks are lining up of the wave, the microwave that's oscillating in the candy bar. So if you measure the distance between them, you'll find that that's related to the wavelength. If you multiply that times the frequency, which is printed either on the back of the microwave or in the door, if you multiply those two numbers, you'll get the speed of light. So you can actually use a candy bar and a microwave to determine the speed of light. Ain't that cool?
Yeah.
So anyways, let's go. Light is a particle. That's the famous equation, E equals HF. They gave you Planck's constant 6.63 times 10 to the negative 34th. This is not an equation I make you guys use. All I want you to understand is that when the frequency of a wave goes up, the energy must go up. They're thumbs up, because they're on the same side, opposite sides of the equal sign, but on the same side of the fraction. In other words, they're both numerators. Since there's no fraction, they're automatically numerators. So F and E are thumbs up, thumbs up. Whereas when I wrote it before as HC over lambda, like that, you see the lambdas in the bottom and the E's in the top. So they're thumbs up, thumbs down. That means when the wavelength goes up, the energy goes down. So that was the equation that we got from Planck. The wave equation, what I call it in this class, is that V equals F times lambda, and you'll see it in your book as well. I do require you guys to use that, but I'm going to stop the share for a second and show you how you can use it really quickly. I'm going to draw something. This will work in all your classes if you're not someone that likes math or algebra. Whenever you have an equation like Q equals MC delta T, that's one from chemistry. Whenever you have an equation where one variable is on one side and all the other variables are multiplied by each other, you can make a circle. And you put the one variable on top, and then you put all the other ones below with little lines separating them. So this one could be M, C, and delta T. But I'm going to use velocity equals frequency times wavelength. So notice that's one solid by itself, so I'll put the V up here, and I'll write that is in meters per second. And then I only have two on the other side, so I'll put this frequency there, and the wavelength here, this is in meters, and this is in hertz. That's the unit we use for frequency. You probably, if you ever hear your station on the radio do a station identification, they'll tell you it's propagating or sending radio waves at 93.7 megahertz. So that's station 93.7 FM, and that's that. Okay. Now here's the neat thing. When I do that, if I want to solve for frequency, I cover up the frequency. Oh, it looks like velocity is being divided by wavelength. That's how you solve it. So if you want to solve for frequency, you divide the velocity by the wavelength. If you want to solve for wavelength, you divide the velocity by frequency. And finally, if you want to solve for velocity, they're next to each other, so they're multiplying, so you multiply frequency times wavelength. So that's what I get you guys to do instead of actually having to do math. So there will be instances where I will say, hey, 105.7 FM is a radio station I listen to. What's that wavelength? Well, you know the speed of light is 300 million meters per second. 3 times 10 to the 8th is what your calculator does. You know the frequency is 105.7 megahertz. Mega means million, so it's 105.7 times 10 to the 6th. And then you just say, oh, I'm going to divide that 3 times 10 to the 8th by 105.7 times 10 to the 6th. And that'll give you the actual wavelength of 105.7. It should be on the order of tens of meters or meters at least. When you do the AM band, though, that's kilohertz. So if you look at, AM 850, 850 means 850 kilohertz. So you'd write that as 850 times 10 to the 3rd. But other than that, it's pretty straightforward. You can do that to find out the wavelengths of any given electromagnetic radiation.
Question.
Yes.
So I took a class in, I think it was called physical science in high school, and I think I was taught that they kind of described light as like this dichotomy between being both a particle and a wavelength.
Right.
So how is that kind of the case, or why is that taught to me, or why was that taught to me, despite it kind of being falsified that it's a particle in the past?
Well, that's the thing. It's actually, and Bohr came up with this. Most people just think Bohr was like a one-hit wonder, but no, Bohr shuffled quantum mechanics through for the rest of his life until he died. He was sort of the king of quantum mechanics. Everybody turned to him for guidance, and he was the only one with the brain power to go up against Einstein, and did so beautifully in some wonderful books. You can read about it. But it basically is something called the principle of complementarity. Not compliment like, oh, you look good, but compliment like I complete you, like Jerry Maguire. So what it means is that light is neither a wave nor a particle, but it has the ability to be either. So in certain experiments, and you don't necessarily know which one you're going to get, but in certain experiments, it'll behave like a particle. In other experiments, it'll behave like a wave. and you don't necessarily know, unless someone's already done the experiment, you don't necessarily know which it's going to be until you do the experiment. So it's a principle of complementarity. It's not sufficient to call it a particle. It's not sufficient to call it a wave. It's a wave particle or a particle wave. So go ahead.
Oh, I was just making a sound of like acknowledgement.
Okay. Yeah, it's odd, isn't it? I mean, it's not something we can say it's like this, because we can't. It's nothing we know of like it except it. So it's really hard to build analogies. But they've done neat little experiments. Like if you shine light through two slits, it makes this cool pattern where it's really bright in the middle, and then it gets dark on each side, and then it gets bright again on each side, then it gets dark again on each side, and so on and so forth. Well, that is characteristic, like you holding your finger next to your index finger that I showed you earlier, your finger next to your thumb. That's characteristic light type properties. So they do this with electrons, and electrons do the exact same thing. It makes a bright spot in the middle, then a dark line on each side, and then a bright spot on each side of that, and then a dark line on each side of that. And you're like, wow, it's really cool. It really is acting like a wave. And then they say, okay, well, let's slow down the particles so they come out at one at a time. And when you look, it'll be individual particles hitting. And as long as you have two of the slits open, over time, those individual dots where the electron hits will make that exact pattern of bright in the middle, dark on each side, bright on each side of that. But if you at any instant close one of the windows, instead of it having two slits to go through but only one, it stops making that pattern, and it acts like a particle again, and just begins a bunch of dots in front of that one split. Yeah, isn't that crazy?
So weird. Yeah, the way that you said that you never really know like whether or not it's being a wave or a particle for sure, unless like you do experiments or something, kind of reminds me of quantum mechanics. Obviously, like I barely know anything about it, but from my understanding, that's kind of like the premise of quantum mechanics, in that like you never really know what the state of it is in.
Exactly. Yeah, and it's weird. Like Louis deBroglie, he won a Nobel Prize too. He wrote his thesis basically on the idea of beauty. So he could not imagine a universe in which light behaves like a wave and a particle, unless matter, which was normally thought of as particles, also behaved as waves. So just based on the fact that that's an asymmetry, he said there exists waves that matter behaves as. And he made his hypothesis, and that's actually the last straw that Bohr got before he did his Bohr model, is he had deBroglie's paper where deBroglie suggested that electron had a wavelength. And then that's when Bohr decided, oh, I'll treat the electron as a wave, and made the Bohr model of the atom. But that was purely on deBroglie saying, I can't imagine a universe in which light, which we traditionally thought of as wave, behaves like a wave and a particle, unless matter, which we traditionally thought of as a particle, also behaves like a wave.
So is that like a theory that people kind of are contemplating nowadays, where matter can either be like a particle or a wave? Or
yeah, we did that same experiment that you do with light. We did that with electrons, so we know it's a fact that deBroglie was right.
Huh. That's so weird.
That's how quantum computing works as well. You can use photons or electrons. So it's kind of crazy. So yeah, that's an intro to quantum, the more complicated stuff. And I also talked about, you can see here how the energy levels, when it drops, it's going to give off photons. This isn't, again, your book, but your book has similar type diagrams. But it explains the emission spectra, the absorption spectra, all that good stuff. I was looking for the velocity equals frequency times wavelength equation, but I guess since I drew it for you guys, here's the spectra that I was talking about. So anybody recall whether these would be emission or absorption? I mean, obviously you could probably read it, but you see how they're black except for colored lines? So that's what we call the bright line spectra, or the emission spectra. So this is what hydrogen looked like. So when I told you that everybody was trying to predict or understand why hydrogen looked that way, see how distinct hydrogen looks? It's got all these little lines, very specific wavelengths. And then you go to the next least complicated thing, and it's helium, and look how different that is. And of course, neon looks entirely different.
Fingerprint.
Yeah, they are. Yeah, they're wonderful fingerprints for chemicals. Whether it be perfect elements or compounds, they're fingerprints. That's why it was so valuable to the chemistry world. Not only that, you can see this is kind of nice. Have you ever been out in the parking lot? The parking lot lights at night look kind of yellow, and then other parking lots, the parking lot lights look kind of blue. Have y'all noticed that before?
Yeah.
We're slowly switching to LED, so they're all white. But if you ever been in a yellowish looking parking lot, those were sodium vapor lights, and notice the lines for sodium look kind of yellow. And guess what the lights are that make a blue parking lot?
Hydrogen?
That would be a possibility, but it's actually mercury. They're mercury vapor lights. So they're actually hazardous when you take them apart. My dad worked for Virginia Power, and he used to get, the ones that they were throwing away to surplus or whatever, we'd get them around their house. So my yard was never dark. But yeah, if you see blue lights in a parking lot, you're always going to be mercury vapor. And if you see yellow lights in a parking lot, they're going to be sodium vapor.
So is there any kind of like pattern that exists across the emission spectrum between elements? Like if you compare them in like a list.
Yeah, well, it turns out you can actually look up the spectra, and there's mathematical formulas for a hydrogen one. There's mathematical formulas for a sodium one. The hydrogen one was Bohr's formula, so you can just look that up in any modern physics textbook or even a calculus-based physics textbook. They'll have it. I think they even have it in the algebra-based, so you can get that formula. But it turns out to find out all these other ones, you have to do some robust quantum mechanics. That led us to Schrodinger and Heisenberg. Schrodinger and Heisenberg both independently came up with with equations that described how atoms and molecules behaved. Schrodinger's was a really simple wave equation. Heisenberg, he was like on a totally different higher plane than everybody. He made a matrix equation that was literally matrices with an infinite matrix is basically a rows and columns of numbers with little bars around the outside. But Heisenberg came up with a system where it was basically matrices, and the matrices had an infinite number of rows and an infinite number of columns. And later we were able to show that they were exactly equivalent, but nobody uses Heisenberg's because, oh my God, that would be horrible to work with infinite size matrices. So once we got that, then we were able to figure out these spectra for all the atoms, and even mathematically with computers, we can approximate them for compounds. So we actually have them not only for pure elements, but for things like water vapor and titanium oxide and stuff like that.
Okay, cool.
Okay. All right. So it talks about this, basically the excitement and decay stuff. It's not that critical. The main thing is, like I said, I wanted you to have some understanding of how these spectra came to be, why it made any sense, what parts of the wave really matter. The last thing you really should know about is the Doppler shift. And what I tell everybody, I've mentioned this in other videos, but if you imagine a person standing in the dead center of the front of a classroom, and you attach two identical slinkies, one to his belt buckle and the other to his back belt loop, and he's standing, of course, sideways to you. As he walks towards one side of the room, the slinky in front of him shrinks and the slinky behind him expands. That's exactly how waves do. So if that wall moved towards me, the light and the sound wavelengths would get smaller. So if the wave moved, if a wall moved towards me, the light and sound coming from that wall would get shorter wavelength. Or if I moved towards that wall, the wavelength would become shorter. Similarly, if I moved away from a wall or a wall moved away from me, that would make my wavelength bigger. And that is basically the Doppler shift. So there's a lot of nice things you can look up. You can see when something's coming towards you, the wave peaks get closer and closer. That's what these diagrams mean. The lines are actually peaks, and the dead center between them would be troughs. So you see all the peaks are running together, and the different distance from a peak to a peak is a wavelength. So clearly the wavelength on this side is smaller and the wavelength on that side's bigger. That's what they use for Doppler radar nowadays. That's how they can tell when rain particles are moving towards this towards the detector or away from it, and how fast they are. We use it to detect how fast a star is moving towards us or away from us. And you can use it to, give people speeding tickets if you want to, because you send light at a car, that light bounces off of the car, comes back to the radar gun, and the radar gun measures the Doppler shift, and from that can tell how fast you're going. It's also the reason that you hear, when a siren's coming towards you, you hear really high pitch, and then as it passes, I know those are great sound effects. I'm a skilled artisan. So when something's moving to you, it's blue shifted. Here the rhyme, blue to you is blue shift, and red is away from you. So that's another way to keep your orders of the electromagnetic spectrum correct. You know that
Is
things
that,
moving through. Go ahead.
sorry, I was just saying, is it called blue shift because blue shift has, well, the blue light has a shorter
Exactly.
distance between the wavelength?
Yeah, exactly. That's exactly it. The blue to you is a shorter wavelength because things are coming towards you. And in fact, if you work in ultrasound, as my wife does, they have blue and red show up on their Doppler on their Doppler when they're doing it. And the blue you can adjust it either way you want, but normally you can adjust it where the blue is things coming towards you and the reds are things going away from the sensor.
Okay.
So it's valuable in a bunch of different fields, obviously. But that's about it. I just wanted to make sure you guys had some intro to. I wanted to make sure you had some intro to quantum mechanics. I don't know what just happened there. Oh, I stopped sharing my video. I hit the wrong button. I wanted to make sure y'all had some intro to quantum mechanics, how light and matter interact, Kirchoff's laws, and then really how to use that V equals F times lambda, because that's one of the 2 times I make you actually use an equation in astronomy. So you should be able to solve problems like if I tell you a certain radio station and tell you whether it's FM or AM, you should immediately be able to calculate what the wavelength would be. Remember, FM means that it's megahertz. So you take the station and say it's 93.8. You say, oh, that's 93.8 times 10 to the 6th megahertz or hertz, and that's the frequency. And the speed of light is 3 times 10 to the 8th. Any questions before I let you guys go?
Nope. Thanks for the great explanation.
No problem. I'm sorry I kept you so long. Looks like y'all stayed there. That's awesome. Appreciate you staying for so long. That's normally longer than I would put my students through in any one video, but I think there's a lot of good stuff, and y'all asked really good questions. All right. Well, I'll let you guys go. Anything else I can do?
Thank you.
Okay, I'm probably going to try to give another one on Thursday at 10 a.m. Y'all are welcome to attend it. I think it'll work. I'm going to send you a link probably Wednesday or early Thursday, but probably Wednesday. And y'all can attend that one too, even though it's for another class. I invited my other class to come to this one too, but no one showed up. So that's another opportunity to interact with me if you have any questions or anything.
All right, thank you so much.
No problem. Have a good one, guys
See you
and
guys.
ladies.